Thank you. Well, welcome everybody. As you all know, is this on actually?
Yes.
Yeah. Yep.
No, it's also on.
Okay. So I'm Neus, and today in this seminar, I'm gonna present the work that I've been doing here for 2 years now on random bit generation with semiconductor lasers, together with Miguel, with David, who was here for a sabbatical year, and with Ingo. So most of you already know or heard already about my work because it was presented in master thesis and so on. So the first part is going to be a little bit of review of previous results. But the second part is going to be about the new experimental results. So I hope everybody's still awake by then. And I don't know what, this work is experimental, so I'm sorry about that, Maxi.
Don't be sorry.
But I don't know what crosses your mind when a person comes to you and say, I'm going to show you experimental results on random bit generation with semiconductor lasers. Most of you may think, okay, this sounds rather technical, rather applied. It's not going to be of my interest. I don't know, but actually it's not like this. I mean, what we do is we start from a complex system, and what we do is want to make it functional for a given application. So in my case, the complex system is a chaotic laser, and the application is its random bit generation. But could be any other complex system, could be applied for any complex system. So there are clear steps to follow if you want to do the real implementation. Everybody agree with me that the first step would be study the fundamental properties, understanding the fundamentals of it. This would be, for some of you, maybe the most theoretical part of the work. But if, as I said, you want to go for the real application, for the real implementation, that's not enough. Understanding the fundamental properties is not necessarily enough to succeed in the application. And here comes a practical realization. This can sound the more technical part, but it turns out that it belongs to the whole physical process. And one needs to take it into account and understand it. It's as important as the fundamental properties. And at the end, what you need is a complete analysis and synthesis of what you've learned, of those results, and develop the application. In my case, a random bit generation. This could work as a summary of my work, actually. But it's not. I'm going to explain everything in more detail. And here's the outline of the talk. As I said, I'm going to start with the basics. I'm going to tell you what are random numbers. All of you might know what they are. What are they used? And then I'll explain a little bit our approach, how to generate random bits from a chaotic laser. Oh, sorry. The factors that we need to consider. And then I'll go to the experimental results. We'll discuss them in the context of information theory. And then I'll be very original, and I'll conclude with conclusions. So let's start. Why do we need random numbers? Well, all of you know that when we buy a book over the internet, the browsers, they use random numbers for generating the keys and for making the secure bot. So in secure communications, they're crucial, but also if you do some Monte Carlo simulations, you rely on random numbers or something similar for that. If you think of online games, they also are based on random numbers. So even though we might not see them, they're present in our everyday life. So basically, we generate random numbers because we need them. And what is a random number? A random number, by definition, is a number generated by a process whose outcome is unpredictable, independent, and cannot be reproduced. So classically, a good random number generator is just flipping a coin, if it's not biased. If you assign heads to 0 and tails to 1, and you flip the coin, many times you will get a sequence of bits that are random. And they're random because if I do that 6 times and I get this result, 1, 0, 1, 1, 0, 1, and I ask you what is going to be the next 6 results of flipping the coin, you might tell me all the possible combinations, but you cannot tell me which one is going to be the real one, the one that you're going to get. Or if I ask you for the 400. So actually, it's a good random number generator. But if you think of the applications that I just mentioned in which random numbers are used now, it turns out that this process is not sufficiently fast or practical if we want very long sequences of random bits. So there are other random number generators, apart from flipping a coin, and they're divided into 2 groups. The first one are the so-called pseudo-random generators. Those are based on a deterministic algorithm, like this one here. And they are based on a seed, on an initial number. And because there's this deterministic algorithm, if you know the seed and you know the algorithm you use, you can reproduce the whole sequence of numbers. Because it's digitized and has a finite number of states. So moreover, there's some recurrences. The whole sequence of numbers can be repeated after a certain, is actually repeated after a certain cycle. And not only that, Marsaglia also showed that it had some recurrences because the pseudo-random numbers, they all fall in hyperplanes of a given dimension, showing that they actually have some recurrences. Still, they can be practical for some applications in which security is not an issue. If you think of modeling, for example, you can use those pseudo, and they are used because, first of all, they're cheap. You only need a computer to implement the algorithm. They're fast because what limits the speed of generating those numbers is only the speed of the processor of your computer. And as I said, they're used in many applications. But if you think of cryptography application, then here this option is, well, this is not even an option. We need what we call the physical random number generators. They're called physical because the source of randomness is based on a physical process, like quantum physics, like thermal noise, optical noise. And here I posted a picture of extracted from ID Quantique. They sell random number generator based on quantum processes. But just to give you an idea, the speeds are not very fast, are of orders of megabits per second. So that's why the use of a chaotic laser is a good approach to overcome first this limitation. But before explaining why, let me show you what is a chaotic laser. Maybe some of you might be asking that at this point. Everybody knows what a laser is. A laser is a device that emits light in a very stable way above a certain threshold where gain and losses compensate. And it just emits light like this thing here in a very stable way. The interesting phenomenon happens when we place a reflective element in front of the laser. Then the light that gets out is reflected into a mirror, let's say, and part of the light can enter back into the cavity. When this happens, this is called optical feedback. The light gets back into the laser cavity after a certain delay time, tau. And then the emission that before was completely stable, now it's chaotic, something similar like this. And these chaotic dynamics can be actually used for random bit generation. But what are the advantages of having a chaotic system? Because that's not explanation enough of why do we want a chaotic laser. Well, this system has a part that comes from the deterministic chaos, but has also some inherent noise. And as you may know, strongly chaotic systems with noise, when we have a small uncertainty in the initial conditions, due to this noise, the what I wanted to say. Yeah, basically happens this. There's a rapid decorrelation of the trajectories. Thus, that small difference in the initial condition is amplified by the dynamics, and you have a rapid decorrelation of the trajectories. So that's exactly what we want if we want to generate bits that are unpredictable and are independent. That's the basics, the main advantage. But not only that, if we think of the chaotic dynamics, as I said, we have fast dynamics with fast fluctuations like this. Those fluctuations are in the scale of the picoseconds. They're very fast. And those are directly related to the final bit rate that I'm going to generate, which is going to allow bit rates of orders of gigabits per second, which are actually competitive to the pseudo-randoms and are in the same order as the pseudo-random generators that I mentioned before. And not only that, it has some practical aspects. A system like this is very easy to integrate in the telecommunication systems nowadays. So it has many advantages while using a chaotic laser. And of course, the people saw this, so the potential of this system. And back in 2008, this man here, Atsushi Yoshida, published in Nature Photonics the first implementation of a random bit generator based on this time two semiconductor lasers. He was able to generate random bits at speeds of 1.7 gigabits per second. And it was the here I listed a few. So this was the first one from Chida. And there's been many more. Here I just listed the ones that I think are more relevant. As you can see, all have different configurations. One of them uses one laser, two lasers, optical feedback or optical injection, photonic integrated circuits. But all of them require a post-processing method. That can be some logical operations, some high-order derivatives, bit truncation, at least one of those steps. And the bit generation rate, it's always of the orders of gigabits per second. So after all these works were presented, then the motivation has been always the same. Everybody wants to present a work with a simple configuration, always thinking of the real implementation of the system. So we want the simplest scheme that requires minimal post-processing steps, because every step means making your final bit rate a little bit slower. So we wanted to have minimal post-processing, but still fast bit generation rate. And that was part of the motivation of our work. We see that all these schemes have a general structure. It all starts with the generation of suitable dynamics. Here is where, if you want to call it the information that we're going to use is going to be generated. As I said, we're going to use a system with semiconductor laser with feedback. And then once you generate this information with suitable dynamics, there's a process of extraction, information extraction. In our case, this is done by an acquisition process. And after this acquisition process, which is the practical aspect of it, then comes the post-processing that I mentioned before. Mostly it's done offline. Not always, but most of the cases. And it turns out that all these three factors affect the randomness of the bits. It's not only having suitable dynamics. You only have to understand what's happening in the acquisition process or what's your post-processing doing. And as I said, that was part of the motivation of our work. We wanted to understand and gain some insight into every of these three factors and how a balance is required for the success of random bit generation. And that's what I'm going to explain now. I'm going to explain in detail what we learned at every step, which is not independent from the previous one or from the next one. But before that, let me show you the setup that we use for that. This is experimental setup. As you can imagine, it all started with a semiconductor laser from a Blana that works at the standard telecom wavelength of 1.55 micrometers. The light that gets out of a laser, it's splitted with this optical coupler, and 90% of the light goes into this branch. In this branch, we have an attenuator that controls the amplitude of the signal, more or less. And we have a Faraday mirror. It's a special mirror that rotates the polarization state of a light 90 degrees. So the light that is reflected into the mirror gets back into the cavity with the polarization state rotated 90% with respect to the one that gets out. And this is what we call polarization-rotated feedback. Many people ask why we use polarization-rotated feedback instead other types of feedback. Well, first of all, because, of course, it generates the chaotic dynamics that I showed you before. But apart from that, it's very practical. This is a real Faraday mirror. It's a very small device. It has 5 centimeters length. And it's very, in fiber, it's very practical. It's basically plug and play. If you think of doing the experimentals, it's very easy to use this device. And not only that, this polarization-rotated feedback, it's very robust in terms of environmental parameters. And by this, I mean that if you have some temperature changes, temperature drifts, they are compensated for with this scheme. So it has basically those two practical aspects. There's been other schemes using other types of feedback and have been proven efficient as well. And then we have this other branch used for detection, where the acquisition part is performed with an oscilloscope of a given bandwidth, 16 gigahertz, capable to sample up to 80 gigasamples per second. And then there's the part of the post-processing that we perform offline. So this setup might look familiar for some of you because it's exactly the same one that we used back in 2011 to generate random bits at speeds of 4 gigabits per second. It was the first setup that used polarization-rotated feedback with a single laser and had been proven efficient to generate bits at a very competitive bit rate. But that was not enough. We wanted to go a step further. The next step for us was to explore the full capacity of this system in terms of fundamental limitations, if any, which mean understanding better the dynamical properties, and some practical aspects, like what happens if you increase the sampling rate, for example. So that requires, as I said, understanding better every step of the process. And we start with dynamics. As I said, chaotic lasers can generate suitable dynamics for random bit generation. It's pretty clear that not all dynamical conditions might lead to the generation of random bits. If you think of a dynamical system that has some recurrences, some periodic patterns, some dominant frequencies, that's not actually the best case for randomness. So to generate randomness, you need some conditions, let's say. The first one would be have a system that is capable to have high entropy. But in experiments, the entropy is not an easy measure. And we can use the autocorrelation function, which is a good indicator in that case, although it's not, it's a linear measure. So thinking in terms of autocorrelation function, what we might need is a low autocorrelation function with a fast decay that can ensure that the temporal correlations are the weakest possible. We also need a broad IFISC spectrum that allows for fast fluctuations even beyond 10 gigahertz. And it's not a condition, but it's something that we have in our system. We have, as I said, the noise present, which is not linearly amplified by the attractor, and we benefit from it. So those are the three conditions that one needs to dynamical conditions. One needs to generate random bits. But it turns out that even when one does not satisfy one of these, you can still have random bits. Of course, depends on the post-processing or the next step. They have to be nonlinear. So that was the first conclusion, or the first conclusion we found. Dynamical conditions are important, but they need to be considered along with the following steps in the process, with the acquisition and the post-processing. So we studied in detail the next step, the acquisition process, where, as I said, all the information is extracted. So it might not be trivial at the very beginning that once you have your chaotic signal, imagine this is the oscilloscope, how you acquire the signal, it's crucial for the process. You can imagine, or you can visualize it as the probability density function, something like this. And it turns out that one needs to adjust this probability density function in a very smart way. So what I mean by this is that the oscilloscope has a vertical scale that at the end defines your 8-bit range. So you have to find the compromise of your signal and what you acquire. Let me explain that in detail because I don't think that's clear enough. So in principle, your signal, once you see it as a probability density function, desirably would look like this, like a Gaussian shape. Like in this case, all the bins are covered, and the 8-bit range is completely covered. There are some saturation points, but they're OK. However, if you adjust the signal such as case B, as you can see here, the last bin and the first bin are strongly overpopulated. Because while we were saving the signal, we cut the signal, generating what we call saturation points. Those are recorded as extrema values. So 8 zeros if you're here, or 8 ones if you're here. And those, once you're going to use them for the random bit sequence, they're going to give you recurrences, too many blocks of zeros and ones. So this is not a proper way to acquire your signal. However, if you do the opposite and you concentrate all your information in a tiny probability density function like this, it's not even good for randomness neither. You're leaving some bins here empty, and that's not allowed statistically. So good results can be reproduced if you control the amount of saturation points such that they're within the allowed statistical deviation. And how we did that in the lab, we basically check and control the amount of information in the most populated bin and the extreme bin, and we controlled that to be more or less the same in all the experiments. I'll show you what happens if you don't take these considerations into account later. But now comes the last part, the post-processing. As I said, there's many ways to do the post-processing. There's different methods. The one we use is bit truncation because it's fast, it's efficient, and well, it's fast, it's efficient, and doesn't require any other logical operations, basically. So what is bit truncation? So once you have your signal, your chaotic signal, it's composed of points. Every point is a 8-bit binary number, like this one or like this one. Bit truncation consists of discarding some of the most significant bits and only retaining some of the least significant bits. So the higher exponents of 2 are removed, and we only use in our case, the 4 least significant bits, and we concatenate them to form the random bit sequence. Why we do that? It's because if you think now of the probability density function that I'll show you before, that originally looked like this, after the bit truncation, we have a flat histogram. Now, all the bins are equally probable, which is something that we want for randomness. And not only that, if you weren't smart enough and you didn't adjust the signal properly during the acquisition process, and you had a probability density function like this, where all the information is compact in some of the bins, the bit truncation to the 4 least significant bits is not enough. You still don't get a flat histogram. And the same happens with the probability density function that has some saturation points or some extra saturation points. Still, it's not ready to be used for the generation of random bits. This does not mean that you cannot use the signals. Maybe you can, but means that you need more post-processing steps to generate the random bits. So that's one of the effects of bit truncation, but it's still visible in other measures like the autocorrelation function. This is the autocorrelation function of a signal from the laser with 8 bits. As you can see, there are some peaks that appear at multiples of the delay time, tau. And those peaks might lead to recurrences in your system. But it turns out that if you truncate the signal to the 4 least significant bits, those peaks are completely gone. They disappear, which is good for randomness. That's actually what we want. But that's not the only information we can extract from the autocorrelation function, because the 0th AC peak contains more information. Turns out that the sample interval must exceed the width of this 0th AC peak. This is what I illustrate here. Here we have the autocorrelation function of a truncated signal, so only with the 4 least significant bits, in a semi-log scale. And it was acquired at 80 gigasamples per second, meaning that the space between the points, it was 12.5 picoseconds. And here in red, I show the correlation value of the nearest neighbors, which is 0.04, pretty small. However, if we acquire another time trace, this time with 40 gigasamples per second, so the points are spaced 25 picoseconds, we truncated to the 4 least significant bits, we made the autocorrelation function, and we plotted in semi-log scale. Now, the nearest neighbors have a correlation value which is 2 orders of magnitude smaller. So what this tells us is that, of course, the residual correlations, even in the truncated data, depend on the sampling rate. So in principle, one could think that a case like this would be better for random bit generation than this one. However, one needs to test and check it before anything, and that's what we did. We went to the generation of random bit sequences. So for that, what we need to do is to require data taking into account, or acquire data taking into account the 3 steps that I mentioned: dynamics, acquisition or digitization process, and post-processing. So the chosen conditions were a dynamical condition where we had low autocorrelation function, a broad area of the spectrum. We control the amount of saturated points that I mentioned before. And we truncated the signal to the 4 least significant bits. That's how we got our bit sequences. Now you need to test them and see whether they're random or not. And for that, we used the National Institute of Standard Technologies batteries, which consists of 15 different tests that check for example, the frequency of zeros and ones in your sequence, and they check whether that would correspond to a random sequence or not. It also checks for patterns and so that. And we used 1,000 sequences of 1 million bits each. So we start with sequences acquired at the sampling rate of 80 gigasamples per second. It turns out that those bit sequences did not pass the 15 tests, meaning that that residual correlation was actually non-negligible. And one cannot simply increase the sampling rate and get random numbers at higher speeds. So we tried again with sampling rate of 40 gigasamples per second. Now, the point were spaced 25 gigaseconds between them that had, as you remember, lower autocorrelation value between nearest neighbors. And the sequences did pass the 15 test. So we generated random bits at speeds of 160 gigabits per second. And at this point, I want to remind you that we increased by 2 orders of magnitude over previous bit generation rate, which was 4 gigabits per second. And the only thing what we did was just studying in detail the system. So we were very happy. OK, perfect. But not only that, it turns out that our oscilloscope provides the numbers in a 16-bit digitization format. So you know that the words can be with 8 bits or with 16 bits. Up to now, we use only 8 bits because the current analog to digital converters cannot work with 16-bit words at higher speeds. But that does not mean that in the near future, these 16-bit words can be used. So just to check the potential of the system, we checked what would be the generation bit rate if we use the 16-bit words for every point. We had to truncate them to the 12 least significant bits. As I said, the post-processing is unavoidable. And we successfully generated random bits at 480 gigabits per second. That was pretty impressive. It was a very competitive bit rate. But now you may ask, OK, you showed the results for a given dynamical condition. Is this the only one? Were you just lucky and you found only one case? Or what's actually the role of the dynamics? Because you truncate the signal to the 4 least significant bits, that might be only noise. Those are very good questions, actually. And to understand a little bit what happened in the system, what we did was checking other operating conditions. So we changed the injection current, the feedback strength. We acquired, again, 1,000 sequences of 1 million bits for every dynamical condition showed here at a sampling rate of 40 gigasamples per second. And we checked what was the number of tests that passed or failed. And that's what we plot here. The color bar represents the number of failed tests. The results that I just showed you correspond to a case here of 50 milliamps and a power transmission of 24.7. And as you can see, close to this point, either 0 or only 1 test failed, meaning that this dynamical condition, even though the signal here is truncated, it's more favorable for random bit generation. Whereas if you go for injection currents higher than 23 milliamps, the number of failed tests is so big that the bit truncation is not enough to overcome the unsuitable dynamics. This does not explain what's happening in the system, but it proves that actually it's not only noise, and dynamics is still present after the bit truncation. So after this, just to remind you what we've done, I'll show you I've shown you some results changing to sampling rates, and you've seen that with 80 gigasamples per second, we didn't pass all the tests, where with 40 gigasamples per second, we did. And a clear explanation might be here in the value of the nearest neighbor's correlation. Is this coincidence? Does this mean that there's an upper limit in the generation rate? And what's more interesting, can we know beforehand what's the bit rate that one can expect from our system? The answer to these questions comes with information theory. It turns out that the maximum amount of bits that one can extract from a waveform at a certain rate is given by the Nyquist theorem. It's not the same Nyquist-Shannon sampling theorem. This is another one. And this Nyquist theorem states the maximum channel capacity for a noiseless channel. And the expression is this one here. where h is the bandwidth and q is the number of quantization levels. To know what values we have to use in this equation, we need to go back to our system and remember what we have. In our experiment, we have an analog system, which is a chaotic laser, with dynamics of a given bandwidth. In this system, signal and noise are undistinguishable. They're inherent parts of the dynamics that we use for the generation of random bits. And therefore, we benefit from a wide bandwidth that comes partly from the analog system and partly from the digitization system, which is beyond the 3 dB cutoff frequency, which would be around the 16 gigahertz. Moreover, we use the least significant bits, and those contribute to the spectral bandwidth with the higher frequencies. So now, taking into account the Nyquist-Shannon sampling theorem, our bandwidth is of 20 gigahertz, and it's the one that we use in the equation. So with a bandwidth of 20 gigahertz, and in the case of the further significant bit truncation, we have 16 quantization levels, meaning that the maximum bit rate that we can obtain according to this information theorem from Nyquist is 160 gigabits per second, which is exactly the bit rate that we obtained. This might explain why we succeed with this bit rate, but we fail when we try to increase the sampling rate. And just to check, if we do the same with the 16-bit digitization, we would have 4,096 quantization levels, and the maximum bit rate is 480 gigabits per second, which is exactly the same bit rate we obtained with our approach. So this means that bit rates beyond the limit established by this information theory do not lead to the generation of random bits. But this does not mean at all that other tests, more sophisticated tests, will find some randomness in our sequences, or some randomness, no, some periodic patterns or some correlations in our generated bits. So still, it's a good approach, it's a good start, but it's not a complete truth or the definite solution. So I didn't want to finish like this. So this work was recently accepted for publication in the Journal of Quantum Electronics. But it's not science fiction, because most of you may think, oh, that's nice, but is it real applicable? Is it can be used, actually? And here I just listed 2 of the other works, which are even more applied than mine, where they implemented the real random bit generator. The first one was in 2010 from a group from Greece, and they used a photonic integrated circuit for generating random bits at 140 gigabits per second, although they use 16-bit words. The other one is more recent, was published, I think, in August this year, from a group in China that I got to meet. And they actually built this random bit generator, and they got it working for 24 hours, generating random bits at speeds of 4.5 gigabits per second. And all these schemes are already ready to be implemented in photonics networks. So to conclude, in terms of random bit generation, we identified the factors to consider. One, we want to design a random bit generator based on a chaotic laser, which are the dynamical properties, the acquisition, and the post-processing. And we've shown how understanding the interplay between them is very important to improve the performance. We also explored the limitation in the maximum attainable bit rate according to information theory, which is very useful if one wants to know beforehand what is the maximum bit rate that can expect from its system. And we've shown that with the proper balance, our random bit generator improved its bit rate by 2 orders of magnitude, from 4 gigabits per second to 160 gigabits per second. And if one thinks in the future, with 16-bit digitization, that bit rate would be 480 gigabits per second. And a more general conclusion, in case you didn't understand that one, we have investigated a cross-disciplinary application of complex photonics, which is a random bit generation, and we have shown how analyzing the interplay between the fundamental and practical aspects is crucial to achieve the functionality. Thank you.
So it's time for questions, comments, remarks. Claudio?
Neus, I understood that the first results of 160 per second were obtained experimentally in the lab. What about the other one? How did you do that? With numerical simulations, or
No.
how did you?
No, actually, the scope gives you 16-bit word.
Yeah.
But that's not, if you think of the implementation, it's not real because it can be used, but it does some digital signal processing. So it generates the 16-bit word with some processing. So what I did was truncate it to 8 bits, which would be the real case, and would be the only ones that can be used nowadays with the analog to digital converters. There's still no 16-bit analog to digital converters capable to work at such high speeds.
But what did you use when you got so when you got the result, you used
What result?
So you say you used sorry, I lost 4 or 8 bit.
8 bit or
16.
So 8, you use numbers with either 8 bits or 16 bits, right? The problem is that the oscilloscope.
From the oscilloscope.
Yeah, the oscilloscope gives you directly 16-bit words, but it gives you 16-bit because it does some internal digital signal processing that you cannot avoid.
So it takes, let's say, the 8 bits from the signal, and the other put something in.
Exactly.
Then you use that, you get a better result. So that the oscilloscope is generating very good random.
The oscilloscope is doing some internal processing that you cannot avoid, and it gives you the 16-bit word. Now the thing is that those 16 bits are not cannot be used nowadays in the application of random bits because, as I said, the ADCs cannot work at such high speeds. So what we did is just use only 8 bits, truncate it to the 8 bits, as would be the case of a real implementation of it. And if you want to think, oh, what's going to happen in the future once we can use the 16 bits?
You try to use the 16 bits.
Yeah.
And you get a better good result.
Exactly.
Even better, actually.
That you could not do in real time.
So this is the result we can have now. But this one cannot be implemented in real time nowadays. We need to have better analog to digital converters. But it shows the potential of the system in the future.
Maybe it's a stupid question, but why do you need an analog to digital converter if you already have the bits?
The analog to digital converter gives you the bits.
No, but the
you have
the scope is a digital one. It will give you bits.
Why? Because it uses ADC.
The scope has an internal analog to digital converter.
So the ADC is internal to the
oscilloscope, yes.
So if it is internal to the scope and is an 8-bit analog to digital converter,
but does the
how they manage to get 16-bit out of that?
They have very good random generator.
I'm a little bit confused.
No, it is a bit confusing. But what happens then, in order to, for example, flatten out any
the frequency response,
frequency, or unflatness, they do some interpolation and digital signal processing, and the outcome of that is 16-bit resolution.
So how an 8-bit plus
8-bit plus.
ADC or 8.
The ADC is 8-bit, the rest is post-processing.
You could also use some lasers with a larger bandwidth, no? Because it will take 20 GHz, but they are with much higher bandwidth in the market already. So it goes with the
it scales with the bandwidth,
It scales with the
the analog bandwidth you have. Yeah, and that's something we learned with information theory. Depends on the bandwidth that it's involved, not only the analog, but of course better analog bandwidth, and digitization bandwidth would lead to higher bit rates, or at least a higher maximum bit rate.
Neus, how can you use a physical random number generator for photography? I mean, you have the emitter and the receiver, but you should have a common key in order to the receiver decode the information. And I don't see it in a physical one.
Sorry?
I don't see in a physical one how you can use it for let's say.
You don't see why with the physical random number generator you can use it for cryptography.
Yeah.
I think the question is how you can regenerate, let's say, in the receiver the same random number sequence.
Well, it depends on the application we're talking about. But at the end, a physical random generator has a part done in the electronic way as a pseudo random generator. I think I don't understand the question.
In the formula of IFISC, you have the only physical information telling you that there is a semiconductor laser is the bandwidth of the laser. I expected to find there something like the Lyapunov exponent or some model of linear entropy or something. So is just the bandwidth is enough to characterize the device? Or is this proportional to some Lyapunov exponent or something?
Well, it depends, because here what we want is we want to know what's not only the amount of information that we want to transmit via this channel, also the amount of bits that we can obtain from our signal. In that case, it scales with the bandwidth and the different numbers of digitization levels. That's also for a noiseless channel. If you have noise added in the system, then the expression is different.
So the only information on the dynamics is the bandwidth is enough. There should be some assumption there. There should be some Gaussian channel or something. There will be some assumption of the statistics of the bits. It's not the same as semiconductor laser than
well,
it's I mean, both are physical things.
I don't know.
So this is not related to dynamics. This only gives you the maximum information that you can have in the channel of that network. Whether you're able to reach that capacity, that depends certainly on the dynamics.
You see that the semiconductor laser is nearly achieving.
So we managed to get to the limit that is possible. So the maximum information has to be such a channel.
I mean, this is only for communication purposes. So it tells you information about the information you can transmit in a channel for communication.
And again, that's great. Can you go to the picture where you have that colors the different with the parameters, the different regimes with them? So here, this one, yes. So that's related to this. So this is the. So as you increase the intensity, for instance, you get more chaotic. Or how does this relate with the dynamical regime? So it's more chaotic to the left, more chaotic to the right, so we have one of exponents as greater to the left.
I can compare this one with, for example, a plot that I didn't show for. This would be more or less a dynamical study where the color bar represents the height of the autoclavation peaks. And in this region here, where the tests were better, like 0 or only 1 failed, they show the low autoclavation peaks in the dynamics. Whereas for 23 or above, the autoclavation height of the peaks was close to 1. I don't know if that's your question. How you ask? So
it's more chaotic to the right.
No.
To the left.
To the left.
So
Yes.
that's good for randomness.
Exactly.
That's
Exactly.
Well,
Here the autoclavation is bigger, and here it's lower. Yeah.
Are the Massago planes part of this battery of these tests? Does any of the tests check the dimension of the Massago plane?
Not for the Neus test has for pseudo-random generators and for random generators. So you have to, once you test your sequences, you have to tell them whether it was generated from a pseudo-random or for a random. The pseudo-random, they check the dimension of your hyperparameters, not the random, I think.
Because there is no reason to assume they will be affected by this theory, right? There is no a priori reason to assume
that they would, yeah.
More questions? Or comments? If not, let's thank our speaker again.